David Smith here with another Flipped Classroom math video. A few tips before we get started. Remember, you can always pause the video to make extra notes or write down questions for when we meet in class. Also, remember to pause the video when I provide an example. Work that problem, then start the video up again and see how well you did. You can also turn on the captions so you can see my words written below on the screen. You can also speed up or slow down the video if you wish. Remember to think hard, follow along, and bring your best brain to the next time we have class. Today's problem involves using differential calculus, that is, derivatives, to solve an optimization problem. Now, this problem you have seen before undoubtedly. It's a pretty standard problem for high school mathematics. So let's take a look. So what we have is a piece of cardboard that measures 15 by 24 centimeters. Okay, just a nice big piece of cardboard. Now what we want to do is we're going to cut out the corners and fold it up and make a box, something like that. So on the piece of cardboard, remember there's just one flat piece of rectangular cardboard. What we're going to do is we're going to cut out the corners like so then we can fold up the sides, and that will make our box, which looks a little bit like a tray here, but we can make it taller and make it look a little more boxy. So now, because this is a rectangle, that means that when we cut out these square corners, the side of them is all going to be x, okay? So it's going to be the same amount because these things have to fold up perfectly to meet at the top corner of the box. So really there's only one x that matters in terms of how we cut up this piece of cardboard to make a box. Now, I started by saying it's an optimization problem. So what we want to optimize is the volume. We want this box to hold as much as possible for this limited resource. So this is it. This is the piece of cardboard we have. We want it to hold the most volume. So here's a statement of that problem. Find x so that the box has a maximum volume. So obviously, if we make x too big, it's going to start decreasing the volume. If we don't make x big enough, the volume won't be very big either. So there's an optimum x. And we're going to use derivatives to find that. Finally, we're going to verify our solution graphically. So there's a function we're going to graph. We're going to take a look at that, and that's going to verify our solution. Okay, so let's get started. So your first task, you need an equation for the volume of the box. And there's some assumptions you have to jump into, and then you can make your equation. So I want you to pause the video. If you remember how we quantify this and how we use the variable x and these side lengths, go ahead and do that. Okay, so we're going to call this the length, and we know that this is 24, but we're cutting out x. This distance here is also x, so it's going to lose two of those x's. So the length is going to be 24 minus 2x. Same with my width. The total piece of cardboard is 15. But again, we're going to cut out x. So what's left for the width is going to be 15 minus 2x. Finally, we need the height for the volume. And the height is just going to be the x. When we fold that side up, that distance right here is x. So this is 15 minus 2x. And this is 24 minus 2x. So now go ahead and write an equation for the volume of the box. All right, let's see how you did. Volume is just length times width times height. So I did my length times my width times my height. Now, we're going to need to expand this equation so that we can take nice, easy derivatives. I mean, you could take the derivative in that form, but it's going to be a lot more complicated. So let's turn that into a polynomial of degree 3. It's going to have a third power, a second power, a first power, and a constant. So go ahead and do that expansion and come back. Okay, so here's what I get. 4x to the third minus 78x squared plus 360x. And I'm sorry, there is no constant in this one because we would have a constant term here with a 24 times 15. But everything gets times by x at the end of the day. So that's why we don't have a constant in our volume. So the volume is a cubic function. So think about what that graph looks like for a minute, because that's going to be an important graph to interpret in terms of our answer when we answer this question, when we verify our solution graphically. But first we're going to do it algebraically. So I want you to think about how derivatives are going to help us figure out what value of x makes this expression the biggest it can be. So before we do that, I want to take one look at the domain for this problem. What can x be? Because it's limited in this case. So let's take a look. Based on length, we have 24 minus 2x. We can't have a zero length or a negative length. So x has to be less than 12. If x were 12, we'd have 24 minus 24 and we'd have zero length. So based on length, the domain has to be less than 12. Now with width, we're restricted a little further. 15 minus 2x has to be bigger than 0, so that means that x has to be less than 7.5. If it's 7.5 or bigger, the width is going to be 0 or negative. We can't have that. Finally, the height, which is x, the height can't be negative. The height has to be positive. So the restriction on the height is that it has to be bigger than 0. So combining all of these, the biggest x could be a 7.5, or it has to be less than, and it has to be greater than 0. So here's a nice statement of our domain. The set of all x such that 0 is less than x is less than 7.5. So that tells us the values of x have to fall in this range. If we get other values of x, they're not valid for our problem itself. So this is kind of like a little reality check, referring the math back to our actual diagram and what we're trying to figure out. Okay, so this is differential calculus. So your first step here is figure out the derivative of the volume equation. All right, so here's what I get. I used v for my volume function. So the first derivative of that function would be v prime, and I get 12x squared minus 56x plus 360. Now, if you recall what we've been doing with our first derivatives, we set them equal to 0 and solve for x. And that gives us points for x where the tangent line is got a flat slope, or the slope is 0. And what that means for our function is that we've hit a maximum or a minimum. It's a turning point. Now, we want to maximize our volume. So that's going to happen at a turning point. It's going to happen at a local max. So what we need to do is set this equal to 0 and find the solutions where we have a turning point, a minima or a maxima. So go ahead and do that. Set that equal to 0 and solve for x. Okay, let's see how you did with your algebra. Here we go. Set it equal to 0. Now, you could factor and solve this expression, but everything in here is divisible by 12. So I made my life a whole lot easier by dividing through by 12. And that gives me just simply x squared minus 13x plus 30 equals 0. This is a straight up product sum factoring problem. I get x minus 10 times x minus 3 equals 0. And then I solve each of the binomials, set them equal to 0, and I get x is 10 for this one and x is 3 for that one. So we have two solutions. Are they both valid? Is one valid? If that's the case, which one is not valid? So pause the video, think about what we've done, look at our work, and your clues are there. Figure it out and come back. Okay, so check this out. Our domain has to be greater than 0 and less than 7.5. So we know x can't be 10. So the solution that maximizes the volume is x is 3. Now let's go back here to our diagram. If x was 10, if this is 10 and that's 10, then that's 20 we're taking out of this side to fold up. We only have 15. So 10 just doesn't make sense with the problem. It makes sense with the math. Of course, it's a valid solution to the derivative of our volume function. But when you map that back to reality, it doesn't make sense with the problem. Okay? So that's how we ended up scrapping one solution. We only have x is 3. So if you want to find out what that maximum volume is, You just take 3 and you put it into the volume equation, you do the math, and that will tell you the volume in cubic centimeters. Okay? So, we solved the problem. We found the value of x that maximizes the volume. Now, there's one more prompt here, and that is verify the solution graphically. Okay, I erased all that stuff, and I gave us our first 2 equations that we developed on the last board. Here's our volume function, and here's the first derivative of our volume function there. Okay, and then I just brought over the solutions. We had the algebra that got us here from the last board, but the solutions, when we set this equal to 0, our x is 10 and x is minus 3. So I went ahead and I drew my number line with my turning points. Remember, the solutions to the first derivative are where the tangent line slope is 0, which is a turning point on the original function. So I kept my 0 in there. I just like that for a reference. Here's a turning point, and there's a turning point. Now, when we analyze these with an eye towards making the graph, the next thing we do is we figure out where the function is increasing and decreasing, because it's doing one or the other on each side of a turning point. So that's going to help us figure out what the graph looks like. So to recall, to figure out whether it's increasing or decreasing to this side of the turning point, I just plug any number into the derivative function and get it out. And if the answer is positive, the function is increasing. If the answer is negative, the function is decreasing. Okay, so I've prompted you for 3 different values to test to say whether it's increasing or decreasing or increasing, whichever one. So go ahead and pause the video and do v prime of 0, which is here. V prime of 4 is between the 3 and the 10, and v prime of 11 is past the 10. So go ahead and do those plugins with v prime and come back. Okay, so what I did is I did my v prime of 0. That gave us 360. That's the easy one because 0 here, 0 there just leaves the constant term from my derivative. So then, so that's positive number, that's positive. So it means all the way, these are my turning points. It's positive here. The function is increasing there. Then we go, I did my v prime of 4, which is right there. I did my math here. I ended up with minus 72. So that's negative. So the function is decreasing in between 3 and 10. And then finally, v prime of 11, did my math there, ends up being 96. The function is increasing there. So it's positive, so it's increasing. So I have my intervals. So now I know that's a turning point and that's a turning point. So roughly, the function is going to look a little bit like that, with a maximum there and a minimum there. Okay, so I already have a confirmation that indeed 3 is my maximum because I can see what my graph is doing. However, the prompt might be verify with the second derivative. So we're going to do just that. So next step, what I want you to do is take the second derivative of the volume function, which means just take the derivative of the first, put that in here, and then we're going to do the same analysis and we're going to confirm our result. Okay? So here's my second derivative, my v double prime. I just have 24x minus 156. Now, as you recall, what we need to do is find the places where the second derivative is equal to 0. Same process we did with the first derivative, by the way. We set it equal to 0 when we solved. So we're going to do that here. I went ahead and finished those steps up for you. I just moved my 156 over, divided through by 24, and that gives me the solution is x is 6.5 is what makes the second derivative equal to 0. Then I went over here and sketched my number line. I put my 0 on it, and I put my 6.5. Now, let's take a look at the difference between these two number lines. This one is where we map the tipping points. Those are the zeros of the first derivative, and we use that to figure out where the function is increasing and decreasing, and it tells us the maxima and the minima roughly where they are. Okay, now when we come to do the second derivative, the solution where it's equal to 0 gives us the inflection point. This is where the function changes from concave up to concave down, or vice versa. So testing for concavity is the same as testing for increasing or decreasing. So why don't you go ahead and pause the video. If you need to look back to your notes to figure out how to do that, and come back once you've marked up this diagram with where our function is concave up and where it's concave down. Okay, so what I did is I tested my second derivative of 0, because that's to the left of my inflection point. So 0 is always an easy number to test. If ever you can, use that, please. And that gives me a value of minus 156. It's negative, so the graph is concave down at that point. Now, I just tested 7, just a little bit to the right of 6.5, and I end up with positive 12. So the second derivative is positive at 7. That means it's concave up at that point. So now what I can do is I can write down here, and I can write up there. Okay? So that also is a confirmation right there. Because if the graph is concave down, then that means the turning point is a maximum. So in other words, here is a random graph that's concave down. Here is the turning point. That's a max. If the graph is concave up, then the turning point is a minimum. Okay, so now we've used the analysis of the second derivative to confirm that this solution, which has a turning point that's a maximum, is a maximum for the function within our range. So that means that that value of x3 will maximize the volume for our function. Okay, so we're going to do this 100% thoroughly. We're going to use what we just figured out here now to make the graph of the function. Okay, I went ahead and just made the graph. Let's talk about it. Make sure you understand. If you don't, make a question and bring it to our next class so I can help you with that. Okay, so here's my work from before. We're going to refer to that in a minute. Here's my graph. I really only care about my domain. Remember, my domain is the set of all x such that 0 is less than x is less than 7.5. So that's my domain. So really, all I care about is x is 0 to 7.5. Now I went ahead and marked a few important things. I put my solution that gives me my maximum on there, and I have my 10 and my 5 just to give us reference. I went ahead also and plugged in my x into my original function, and that gives me my volume when x is 3 is 486 cubic centimeters. So I scaled my y-axis, it's actually my volume as a function of x-axis, appropriately. So my parabola, my power function, my cubic function, has a local maximum right here. Now let's contextualize this. If you were to put that whole graph in Desmos or your calculator, you're going to see that the graph is going to continue on down that way forever, and it's going to dip down below the x-axis, and it's going to continue on up that way. So that's the pure function, but our domain limits it to reality, which is just this section of the graph. Okay, so now let's take a peek at what we learned from the first derivative and what we learned from the second derivative. First derivative, the function is increasing until 3. And that makes sense. Check it out. The function is going up, 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 increasing till this turning point, to the maximum. So this makes sense. We are increasing, like so. And then from 3 to 10, we are decreasing. And that makes sense too, because the function is going down to the right. So it's decreasing. Now at 10, it's going to have a turning point, and it's going to start increasing again. And that's why I've drawn this dashed line representing what the function does. It's just not a solution to our problem. But the function is going to dip down, and at 10, you're going to have your second turning point, and it's going to start increasing again. So that's what the first derivative told us, and it matches up with my graph. Okay, taking a look at my second derivative. That was this number line. Now let's mark our inflection point, 6.5. So that inflection point is right about there. And what that's saying is that this function, first off, it's facing down, concave down. From 6.5 on back, it's concave down. And that makes sense because from here, remember, this is just going to keep going down forever. So from this inflection point this way, the whole thing is concave down. And then this inflection point is where it starts to become concave up. And since this graph is going to go all the way up forever, it's going to be concave up from 6.5 on. Okay? So that's the second derivative, also informing the graph. Now, a lot of bits and pieces all in there, but we used basically everything we've learned about differentiation, and we applied it to an optimization problem where we figured out what the optimum dimension for that cardboard cutout on that sheet of cardboard to make the most volume for a box. If you still have questions, write them down now and bring them to our next class. You can also watch the video again and perfect your notes. Finally, if you enjoyed watching my video, please click the like button down below. And if you'd like to help me grow my YouTube channel, please click subscribe.